what we're doing. Hey.
I have 3 minutes till. What time do you guys have?
You take your time.
Yeah? How are you feeling?
I'm okay. The walk with the dog was fantastic.
Yeah, clear your
It was
head.
like, I don't know, 19 degrees, sunny, clear air. I didn't cough at all. It's like rejuvenating.
Wow.
I didn't go to Duncan. Just went Tamarack.
Tamarack.
It was fantastic.
Yeah, they were
I'll tell
probably
you.
plenty happy.
Oh, they were way happy. They ended up, I'll tell you more about it. We ran across another black lab with a red collar that, looked like ours did 4 or 5 months ago. They came.
Good.
Thanks for checking on. Yeah, so what we're doing is we're abstracting individuals and turning them into numbers. And when we do that, you're one removed from the identity of the organisms. But part of what we want to do when we're working in ecology, or really in any science, is to abstract things. By what I mean by that is you want to be able to come up with general ideas that translate to different settings. Because if we have to analyze every setting, every unique event, we're doomed. There's just too many of them. We need to be able to say, this is how these things work, so we can apply them under other circumstances. And that's why we use models. All models are really is a representation of a fairly complex hypothesis. Hypothesis is what do you think of hypothesis?
Really specific guess.
A really specific guess. Okay, any other potential definitions of hypothesis? Where did you learn what hypothesis is? An educated guess. And where did you learn that? High school. And in high school, we don't seem to be able to purge that. And it's a terrible definition of a hypothesis. It's not a guess. Guesses are derived without understanding history and legacy. You get to a point in an investigation where you think you know what's going on. That's not a guess. More importantly, a hypothesis needs to be able to explain something. You can't believe how difficult it is to get students, or frankly, well-established scientists, to do this. You get called to the Washington, D.C. to sit on a panel. And on that, this is held by the National Science Foundation. When you're on that panel, you review the proposals from across the nation that want money from the NSF. And these are, this ranges from Stanford to the University of Montana to Carroll College. And you're reading his proposals, and then you give to all this panel of scientists what you think about the proposal. And you cannot believe the number of proposals that have our hypothesis is that temperature will go up. Okay, let's think about that for a minute. They're proposing that something's going to happen. So it is obviously coming from some sort of history of understanding. But there's absolutely nothing explanatory about it, right? It's not telling us why or how or anything. It's just something's going to go up. So if you're proposing that something's going to happen tomorrow, what is that? That's not a hypothesis. It's a prediction. Hypotheses need to have explanatory power. They need to explain something. The best hypotheses have the word because in it. Temperature is going to go up because radiative forcing is going to change as a result of changing forests to fields. Well, now there's nothing you can test. You can go after it. Is that really true? So with the word because, a hypothesis suggests that you understand a mechanism. And with models, we're going to try to put together a mathematical relationship where the math involved is the hypothesis. And then we're going to see whether or not, when we collect data, does it fit that model? And if it doesn't, it means the hypothesis is not very good. It needs to be tweaked. So we make it a different model, and we apply it. Well, that's a better fit. So when we talk for this period and then next Monday, we get back together, about these models, there are 8 terms in them that we need to be able to handle. We know the 4 down the left-hand side, right? We need some definition. What's I? Yes, that's the term we use for it, and I'll give you the definition. These are all arrows, so definitions all start with what word? Rate. The rate of, take it. That's correct, but what do you define it?
The rate of individuals moving into a population.
Excellent. And E? Excellent. E? Anybody? Anybody louder? The amount? The amount is a pie. You need a rate, right? The rate, what? Take it home. What?
Rate of individuals moving into a population.
But you need to be more specific. In a population, which is just that everybody is giving birth is contributing to be.
Per individual in the population?
Per individual, that thing, right? Because what we're not trying to say that if you have a bigger population, it's going to have more births. Well, there's more females, meaning they're bigger. We want to know what's going on with the individuals inside of those populations of a given size. That's why we're keeping track of births per individual, usually it's per individual female. D then is the mortality rate. What do we use to track mortality over lifespan?
Life expectancy.
Yes, and what were the curves called? Ridership curves, right? Remember they had different shapes. So the humans, it was highest of ridership when you're young and then tails off as you get older. But that's not the case for all organisms. Okay, so these on the left we got down. And in fact, we know this one too. What's this one?
Number of offspring per
Number of offspring per individual. Yeah, but what do you mean number of offspring? Okay, that's correct. If I think offspring as the result of the balance between birth and death, right? So it's the number of offspring per unit time, but it's really D minus D, right? Because both these things are happening. Organisms are birth and in the population, organisms are dying. And this, the term for that is what, or what do we call that? Why do you keep putting your hand up? That's just old behavior, just talk.
per capita growth.
Yeah, per capita, remember that, per head. Per capita rate of growth. I hope. So is R a constant or a variable? What's the difference? Say that loudly.
Constants stay the same.
Constants are values that stay the same. They're always the same number. And we use them in equations. What's a variable? Bill?
Something you can manipulate?
Variable is something you can manipulate.
I mean,
Well, you might manipulate it or you might not. But what does the essence of the word variable mean?
It will change.
It varies, right? And when you think about a variable, it can have different values, right? So let's say the variable's height. It could be 6 feet, it could be 5'4", right? But if the constant temperature is 60 degrees, then that number doesn't change. So is R a variable or a constant? Think about a population. They're out there doing what they do.
It's variable,
Why would you call it a variable?
because it's changing all the time.
What is?
People dying, people being born.
But if they're being born and dying at the same rate,
Well, if they're at the same rate, then it'd be.
then it's a constant, right? So to answer the question, is R variable, you have to know what's going on with B and D. Are they balanced with each other? Are they constants? We have to think of this as a variable that reflects the conditions out there, and that's why we also call it the realized per capita growth rate, because it's what's actually happening out there. And the only way we can get R is to get B and D. Remember, we use age structure to get some idea about whether or not things are growing or shrinking. That doesn't give us R or D. Sorry. That doesn't give us R, we give D or D. Now there's one other, let's think about it this way. If we had R on the x-axis, or on the y-axis, and let's say we had population size, N, on the x, what does that look like? Asking yourself, if you're an individual, female, in that population, is your propensity to give birth greater or smaller if you're in a big population or a small one? If you're an individual in that population, is your propensity to die bigger or smaller if the population is small versus big? What's the issue? What changes with population size?
Maybe the number of resources.
Maybe.
Food and water.
Well, what if they don't change? I think you're right on the right track here, Raymond. The idea is that resources are an issue. Are resources more available or less available to an individual if they're in a big population versus a small one? If you're an individual in a big population and there's a set amount of resources, you got to compete. Your fellow members of your species are going to want those resources. If the population is small and there's 10 pounds of stuff available, you get more than if the population is large and there's 10 pounds of stuff available. So when we think about the changing size of a population, we have to think about its demands for resources. So would you expect R to be high when the population is small or low? Would you expect R to be big when the population is large or small? Think about your scenarios. You've got a small population, you're a female in that population, and you're trying to procure resources and have babies. Or you're in a population that's really big, and you're trying to do the same thing.
Probably be a higher R rate. Higher rate because there's more resources.
Higher rate, that Dan argument, higher rate because there's more resources when the population size is small. Does that make sense to everybody? So I'm going to graph it, right? I'm going to have here say population is small, right? Down here is 0. Now there's something funky about our graph here. You can't get to the origin. What happens when n is 0? They're extinct. We lost our population and lecture's over. So we can't do that. We got to have it just be slightly off the axis, okay? So that'll put it up here in the higher range. Now if the population grows, and so there's say the same resources available, bigger population, the ability to turn those resources into new babies, and the propensity, that's going to go down, and the propensity to die is going to go up because there's fewer resources, and as you get older and you can't compete, you might not get those resources, you end up dying. So that would suggest the balance between birth and death is going down, right? And it's going like this. And if we keep plotting it, it's going to go like this. So here's R is 0. This is when R is negative. What happens there? How do you get a negative R?
People are dying, or individuals are dying faster.
The rate of mortality exceeds the rate of birth. And if that's the case, your population size is going down. Right? So if you're down here, you're going to move back that way. Right? Which means you're sliding back up that line. So there's something, and if we draw the line here, it looks like this. So that just means it's a linear relationship in the sense that as n gets larger, R gets smaller. Because it's harder to turn those resources into new babies per individual in the population. Because there's more of them. So we would expect larger populations to not be growing nearly as quickly per individual as big ones. Right? And in fact, really big ones might be shrinking because they've overshot their supply of materials. they're facing decline. Sometimes those can be catastrophic overshoots, and there's mass death, and that's not linear. But the model we're suggesting here is every individual added on acts the same, and the response and need for resources. Okay? So if you think about it, what would be the conditions under which an individual in this population could run at the highest possible reproduction rate capable? What would those conditions be?
Low population, high resources.
Effectively unlimited supply, right? What if you gave the population as much resources as they could ever need and actually just give to them in excess? What would the reproduction rate be then? What would happen? Okay, space. If the size of the population gets so large that you're losing habitat, then you can't occupy and reproduce. But what we're going to argue is that space is a resource. Let's throw that in there with water and food and everything. They got everything. Generation time, dance. Predators.
I was gonna say disease.
Disease. Excellent. So you're starting to see both external limits on the rate at which population can grow. That's a species interaction. Disease and predation. What we're doing right now is we're saying let's have one species, one population, isolated in its perfect environment, and let it grow as quickly as it can. What's your argument, Dan, regarding generation time?
You can only have so many offspring in a certain amount of time. Like humans can only have a certain amount of offspring. You can't have 3 days in a year. Your body won't let you.
Right, so there's got to be something about the biological character of the individual species that is limiting its potential to grow. Some species just grow more slowly. Remember, what was the number one determinant of generation time? Excuse me?
Body size.
Body size, right? Big things take more time to develop. So even if you're giving them all of the resources they possibly can use, they're maxed out at some point. It's intrinsic. You know what the words intrinsic and extrinsic mean? So you don't know if you know what.
And it's inherent value versus value applied to it by something else.
Yeah, it's basically the idea that this is something internal to the entity. It's intrinsic versus extrinsic, which is that with which it interacts or that which characterizes it from the external. So if it's intrinsic, if you're just intrinsically a really competitive individual. I mean, in fact, I've always been that. I was born. Some people, I was born with it, right? And this is the same idea for different species. An intrinsic character is something that they've evolved over time. It's who they are. Extrinsic might be something like, oh, the rains didn't come. So that changes the rate at which population grows. But under these sort of, frankly, made-up conditions, optimal resource availability, completely unlimited opportunity to grow, you are limited by your intrinsic growth rate. And that's what R sub m is, R max. We sometimes see it as Rm, and that is equals an intrinsic growth rate. So that's R running at full speed. Where is it on that graph? Where would it logically be on that graph?
All the way at the top.
Yeah. All the way up here. If you could somehow take away all of the influences of N and theoretically hit this axis right here, you'd have R max. When you have no organisms, unlimited resources. Of course, if you have no organisms, nobody ever reproduce. It doesn't make any sense. in calculus and in mathematics, you'll address issues called limits. Have you guys heard of these, limits? Like imagine this idea. I was telling you, I want you to go from here to the iron horse. And I want each step you take to be 1/2 of the distance to the iron horse. How long will it take you to get there? You'll never know, right? Because when you're a millimeter away, you can only go 1/2 millimeter. When you're 1/2 millimeter away, you can only go 1/4 millimeter. It's theoretically impossible to get there if every step is 1/2 of the remaining distance. But you're so stinking close, you might as well be there, because you can just put your hand out. Get here. So in mathematics, that's called a limit, where you let x approach a value, but it's never actually going to get there. And so in this way, we're letting n approach 0, but it's never actually going to get there. And r is going to become the intrinsic growth rate. And so population ecologists will go out there and they mess around with the numbers of individuals in experimental plots, and then they keep track of r, to try to plot this line and figure out what is their highest growth potential. And that's when you get into things like, we were talking about this before, the panda bears, how finicky they are in terms of reproductive conditions and how hard it is to rebuild a panda population. That's in part due to their intrinsic rate of reproduction, and in part due to their habitat and behavior requirements. Okay, so that's R max. Now, is there any particular spot on the n-axis that you're just dying to know about? The answer is yes. Which one is it? Where's the cool spot on the x-axis? Think about your population behavior. From the x-axis up, what's the population doing? It's what? It's growing. Why?
Is the number of individuals.
Say it again.
Number of individuals.
Yeah, but that could be due to immigration. Need a mechanism. Tell me.
The births are greater.
Rate of birth is greater than rate of mortality, right? What's happening below the axis? It's negative, right? What's happening right there? You got to be way louder.
Death is greater than birth.
Right there, we go back over here, R is 0. If R is 0, B equals D, because B minus D is 0. That's the size of the population at which the population doesn't grow anymore. It's met some population size that birth and deaths are in equilibrium and the population isn't growing or shrinking. That's a funky number. Right? I mean, if you want to maintain a population of a certain size, you'd like to see B equal D, R equals 0, and your N, what happens to N? Louder?
Stays the same.
It stays the same. N is constant, right? So think about this plot. Tell me how to draw this one. Here's time, and here's N. We're just tracking, that's a new word. We're tracking the population size with time, knowing that it's behaving this way. Okay, so as population gets bigger, growth rate slows down, and it gets too big, it'll go negative. What does N look like? Remember when we talked about a linear plot? We said if you have time down here, you go from time to t plus 1, and it increases and always adds the same amount, the change in y for every change in x, it'll be linear. Is there a constant slope on this line?
Yep.
Is it really? What about the rate of change in this number compared with population size? We're plotting right now the rate of change. R causes N to change. Here, R is causing N to change quickly and positively. Here, R is causing N to change slower, but still positive, and down here it's changing it negatively. So the rate of change is not constant as you go through time. It's changing because populations are experiencing feedback from their environment saying there's not enough resources out here to be successful, more mortality, fewer births, and so that's not a linear plot.
Is this one line goes like kind of like weekly and stuff? Cause like, it'll go like up because it has a lot of resource, then it dips down because of the huge resource, then it'll go back up because that population got small and like have more resources again.
Where are you?
It's gonna plateau.
You're out in the plateau somewhere. Why does the plateau happen?
You get carrying capacity.
Because you hit some amount of organisms at which the population rate doesn't change, or the growth rate, I'm sorry, the population number doesn't change. The plateau is a flat sill, right? Where is that on here? Where should I draw that?
Be everywhere, it's just a horizontal line.
Who's talking? I can't. Jared?
It doesn't matter, the number can change, but wherever it is, it's a horizontal line all the way across time.
So are you suggesting it looks like this?
If the birth rate equals the death rate, yeah.
Yes, but we're starting here at time 0. Does it automatically go up there?
No.
Kelly Louder, where's your plateau?
It'll like start at the 0, then it'll like gradually like go up and then plateau.
What'll start at the 0?
Remember?
Well, you were talking about a period of time in which things would plateau. If it's going to plateau, what is the situation? If N is staying constant, what must be the situation?
When it hits the resource amount, it hits the top of resources.
It's hit some maximum number of resource availability, births equal death, R equals 0, and N is constant. And where does that occur over here? N has to get big enough so it hits that spot right there, right? So we know it's not at the very beginning, it's sometime into the game. When N's gotten big enough over time to get to where it's plateaued. And I'll tell you what the rest of it looks like. It looks like this. It's called sigmoidal growth. All sigmoidal means is it looks like an S. Now let's see if this makes sense. If you're down here and you look at the change in N in a very short amount of time, it's going up. But then it's going up really quickly, right? And then as it gets bigger, that change in N flattens out and flattens out and flattens out until it's to 0. And that's what this is saying. So I needed to have drawn this so you can see it's really steep when it's low, and then it flattens out over time. Because the rates of change are really big when the population is small, early in the game, and then as the population gets bigger, it gets to that spot right there. And that spot is called K. And it's called the carrying capacity. And that's right here. And that makes sense. You can't, in a world of unlimited resources, you're going to grow at R max. And we'll talk about that in a minute. But when there are limited resources, there's going to be a feedback onto the energetics. Rates of birth and death are going to differ. And as Kelly was suggesting, you could overshoot this thing, and then now your N is bigger than K, and you're into this zone, right? And your R is negative. Then it goes back down, and it does this thing. And really, that's how most populations act. They kind of bounce around K. The deviations don't tend to be that large. But they're kind of hovering around at K, and we figure out the K by fitting a line right through that variation. It's really important to know carrying capacities, because if you're going to be responsible for a herd of elk in the national forest, you need to have some sense of what that carrying capacity is. How many organisms can we support out there compared to how many are out there now? So they're really important feedbacks on the growth. Okay? So that's what k is. Now what happens if you look at 1 minus n over k as you go from the left to the right? What happens to that term? How do you answer that question since I'm asking that of you? What do you do? How do you go through that process? Okay, so the professor's asking, what happens to this term as n gets larger? One of the way you do it is you throw in, well, what if n were really, really, really small? Then that'd be a really, really small number. K is some real number. You know, really, pretty much like 0. Right? The fraction would be so small that this converges on 0 early in the end. So when n is really, really low, this thing acts like 1. Right? But as n gets bigger and bigger and bigger, and in fact when n equals k, what is this thing? 0. So this is a term that we're going to use later when we're trying to create a model that looks like that S-shaped curve. You can think of it as a dampening factor. If you're growing at R max, but you're applying this term to it, then you're letting, okay, let's model it like, okay, you're gonna grow at R max, but I'm gonna shut you down as you get bigger. And in fact, if n is greater than k, then that's a number greater than 1. 1 minus a number greater than 1 becomes a negative number. So again, these are just modeling attempts to show mathematically how populations are acting realistically. Okay, any questions on these things? Because what I'm going to do now is I'm going to switch on to the PowerPoint, go back through it, but a little different. But before we do that, let's make sure we're all good on this, right? What is going on in your brain that is causing you a problem?
Is K always 1, or is that just an example?
Say it again.
Is K always 1 in that, or is that just an example?
No. K is a number that we don't know. And it depends upon your population and your species and things like generation time and body size.
The 1 minus nk, I'm still a little uneasy about that. Could you explain a little bit more?
Yeah, so here's what's going to happen. We know that that S-shaped curve really comes because R changes. So one way you could model that would be to put R in there and then figure out how R is going to change as n gets bigger. But to get R, you need to know B and D. And those are hard numbers to get. Instead of using that modeling approach, what they do is they model using R max, and then they put a buffer term on it, a dampening term. So let's imagine it's running at R max. But then as it gets bigger, we'll crank R max down, and we'll get it so that that dampening factor will shut growth off at some population size. And the way you do that mathematically is to tack 1 minus n over k onto R max. And the way you always think about what's the influence of a term in the parentheses is you look at the variable. Is k a variable or a constant? You know? K variable or a constant? It's a constant. It's a number that we've figured out that is k. Now k could change if the world in which the species are living changes. But for a given study of a population, k is a constant. So when you look in there, look inside that parentheses, what's your variable?
The in the population.
It's
size.
n. So then in your brain you say, let me tweak n around a little bit. Push it way down to the bottom and push it way up to the top. If n is a really, really small number, then n over a real number, it's a fraction. You know, 1 over 2 is small, but 1 over 4 is even bigger. So that when you push the top number down, that number gets smaller and smaller, right? So as n gets smaller, it approaches 0. That's another limit idea, right? So that if n is really, really small, it's like n over k doesn't even exist. And it behaves like it's 1. Now do it the other way around. What if n is really, really big? Then that's a huge number. And 1 minus a huge number is some big negative number. And then you could ask yourself, what if n is equal to k? That's 0. And that'd be where it stops growing. No, so what we're going towards is the product. What does product mean? Yeah. What does product mean in math?
Using the answer of adding two things together.
That's the sum. When you add things together. What's the product? Two things are multiplied together, right? So we're gonna work with the product of R max and the dampening factor. That's the way we're gonna grow this population. You can see that that's running along at full potential, and if this is just 1, well then it's growing max. But as n gets bigger, the expression becomes a smaller number, right? And that's just the way they decided to model this. Instead of using per capita rate, they use the intrinsic rate. Okay? Anything else? All right, we'll go back through this, and I'll approach it a little differently. I'll approach it the same way and then a little differently. Usually, so that shape of that curve right there is called the sigmoidal, when it's S-shaped like this. But the term that we use for this model is logistic. It's called the logistic growth model. And that logistic growth model is this. dn over dt equals R max times 1 minus n over k. What's dn over dt? That's back. You got it? You can give me a version of it. What if those d's were deltas instead? The delta standard. Anybody? Delta? Changing, right? And in calculus, what you're questioning is, what are the instantaneous changes? So that delta t is another limit. It's, you know, I had my calculus teacher would say, go ask your mother for a small number. dt is smaller than that. It's the idea that you're creating a separation in time that's so small it's almost instantaneous. So you could get a continuous number. Imagine a situation where you had a curve like this, and you wanted to know what the slope was between 2 points. Well, you could choose a point here, and you could choose a point here, right? And then you calculate the rise and the run, and you calculate the slope. Well, what if those points were closer together? Then you create that slope. What if they were closer? So when you are doing this, you're running a line between 2 points on a curve. That's called a secant. What do you call a line that intersects a curve at one point, right out of your 10th grade geometry? Nobody knows. It's a tangent. So if you could drive a secant, which is a sort of obscured my point. If you could drive a secant like this, and when you take calculus, this is what you're doing when you're doing differentiation. That's a secant, right? It's hitting at 2 points. Let's drive those 2 points closer and closer together so that they're so close to each other that they might as well be a tangent. That's an instantaneous slope. That's a rate of change that is happening right now. Now, it's impossible for it to be an instantaneous slope, right? Because if there's only 1 point, you don't have a slope. But if the distance between them is so small that they're effectively the same thing, then delta n over delta t, which we get from the secant, because we chose a big chunk of time between them, where delta t is down here, we get delta n off of that. But when you jam this thing together so that it becomes instantaneous, the calculus notation is dn dt. All it means is the change in numbers per change in time, but it's done really quickly. It's continuous, so that you can just ride your tangent all the way up this. See how it's low, then it gets really high, and it's really high, and then it flattens out, and then the slope is 0. So that's the rate of change. The model is about the rate of change. It's not about the numbers that are there, right? And so this is called a differentiation. In calculus, you differentiate to determine rates. How many of you are planning to take calculus? None of you? How many of you are getting a degree in science? None of you. 2 of you. You shouldn't get a degree in science without calculus. Okay, so this might be the only place you run into much calculus. It's really interesting because there were these 2 guys interested in completely different questions. One was a German named Leibniz. The other one was an Englishman named Newton. Newton wanted to know whether or not the distribution of mass would influence gravity. So you have something with mass 1 and something with mass 2. Would it matter if the mass over here was spread out like in a big beach ball, and the mass over here was really small like a golf ball? Or is it just the mass? And in order to answer that, he developed calculus. But at the same time, this German, they didn't even know each other, developed the same math with slightly different notation. And it's pretty extraordinary. It says something about where the brains of these type of people were. They were on the cutting edge of thinking, and they came up with it at the same time for different reasons. So this is saying, let's let the change in the number per time be the maximum rate dampened by this 1 over n minus k term. So that you can see when you're at k, the rate of change will be 0 because n over k is 1, 1 minus 1 is 0, the change is 0, so there's no change. Over here, this should be a pretty big rate of change. Well, if that term is really small, then it's running close to R max. It's over here. So this is showing you how R changes as it goes through this progression, and this is showing you how they mathematically model it. You see in here, they don't use R. They just use R max and then dampen it. Idea is the same. This is an abstraction. The reality is here. R is changing, but this follows the curve quite nicely, right? Suggesting that R is some fraction of R mass as you get more and more individuals involved. Okay? Anything else before we go PowerPoint? All right. Now we'll just have the technology bog here. One part of this story that we haven't talked about is how R max behaves. And it's really quite interesting. Let's see, where are we? Let's do this one. Yeah, that's us. Okay, so this was where we were talking about the idea that the per capita rate of growth is B minus D, right? Making babies and generally older individuals dying. And so the R is the number of offspring per individual. Could be positive or negative, sometimes called the realized per capita rate. And this is a linear model if R doesn't change, right? You're always adding the same number of organisms per time to the population. And R doesn't depend upon the size of the population if R is constant, right? But we've made the argument over here that R is not constant because rates of births and deaths change. So a linear model only works if R remains constant. If R changes, then the slope changes. That's not linear. Okay? So here's our population size for linear growth. And we argued that it'd keep doing this forever, right? And then I showed you that if we always add 3, it doesn't matter what size the population is, the population goes up by 3. That's linear, right? Then we went through this curve. And this is the idea of, well, does R really stay constant over time? It doesn't. And we know it doesn't because when the population is low, each individual, population size is low, each individual has access to more resources. They're able to translate those into offspring. It's really common that if organisms or populations hit a bad year, they won't reproduce. Like particular trees, if it's too dry, they'll just skip the fruit production. And farmers know this beautifully. They understand entirely how resource availability translates to products. And it's a big deal. It's all about reproduction. Fruiting bodies are reproductive bodies, right? So we know that they do better when the population sizes are smaller because there's more resources for them. And then that declines, and we could draw this plot. Now if you're down here at this plot right here, you're in a situation, a population size, where the R value is negative, so your next step in time would probably move you back to the left and would be getting smaller, right? And you might continue to move back to the left to the point where now you're up into the zone where R is positive again because N is small enough to support births in excess of death. And so what is that interesting point right there? That's the carrying capacity, right? Now let's talk about what that really is. So there are two ways to define it. The best way to think about the carrying capacity is that it's a characteristic of the environment, right? The environment is going to carry a population of a certain size. So we could think of it as the characteristics of the environment that determine the population size at which growth stops. Okay? So you could think of this as all the growing of the population size, and it comes up to some maximum value, and you can't get it any bigger because of loss of habitat or human development or weather or starvation or predators or hunting, disease, parasites, all these things, right? This is going to be the size of the population that can be supported by the surrounding environment. Okay, so it's a characteristic of the environment, right? Now there's another way to think of it. If you think about it in terms of modeling, so here's the sigmoidal curve, okay? So here's time. You can see that it climbs up quickly early and then it flattens out to a constant value. If you go from that plateau back over to K right here, then the carrying capacity is the population density or size. That should be size, right? Because over here it just says number of individuals. Population size at which growth stops. So that means carrying capacity is a characteristic of the population. Those are two different views. One is saying a carrying capacity is a characteristic of the environment. The other one is saying that the carrying capacity is a characteristic of the population. In truth, they're both accurate, because we use K over here to model populations. And so this would describe the population density at which that term goes to zero. Right? So you're going to give it to the model and say, yeah, it's a characteristic of the population. But in truth, it comes from the environment. Right? The carrying capacity are the set of conditions that determine what K is. And K is the population density at which growth gets to zero. Kelly, what do you think of this right here? Okay, so earlier Kelly said, is this where things go up there and they wobble and they go up and down, stuff like that? And then we got to the idea that that's out there on the plateau. So is K the maximum population density size? Why not?
Because you can have more, or whatever the species is, go over K, then you just have a higher down rate. So
Because you can have conditions when R is negative, right? N is greater than K, R becomes negative, and they wobble around there. So this is not, this is not really accurate. That would suggest that you can never have population sizes where the population is declining. We know that's not true. So don't think that K is the maximum. K is the value at which B equals D, and rate of change equals 0. Right? So this sigmoidal population growth is what we're going to talk about when we go into logistics. And here's that point I just made, or that Kelly made earlier, is that things overshoot. And when they overshoot the carrying capacity, things go negative. R goes negative. So carrying capacity is not the maximum population. It's the population size that can be sustained, where B and D are equal. Okay, now we're going to switch models. What we started with over here was B minus D gives us R, and R could be positive or negative. It could change, right? But that growth model that we used before it's the difference between births and deaths, and it really doesn't require that we know the population size, right? If we know the rate of birth and the rate of death, then we can figure out what R is. But there's a type of growth that depends upon the population size. So when we made the model for this linear growth over here, using this linear equation, we didn't know where we were on that graph. We didn't know if we were down out here. Oh, that's time. If this is population size, we don't necessarily know where we are on it, but we know what B and D is, and we know what our growth rate is. Exponential growth is not the same thing. Read that. And I've colored the keywords, right? That if it's a constant fraction, proportion, then it does matter how big the population size is, right? Let's say you're adding 50%. And if you're a population size of 10, then you're adding 5. But if you're at a population size of 100, you're adding 50. So you can see that growth model means that we need to know an R value that we can use, and we need to know the size of the population. So it's not a constant number of offspring per time. It's a constant fraction of the amount that are present. And that's exponential growth versus arithmetic growth. The arithmetic growth is adding and subtracting. We were talking about this before, like when you're going to go from here to downtown. We think about 1, 2, 3, 4, 5 steps, or a quarter mile, half mile. But if things are so big, it makes sense more to ask how many 10 times away are they? Is it 10 times from here to there, or is it 100, or is it 1,000? Then you're jumping in multiples. And that's the error. That is the geometric. That's the logistic. That's the exponential. We think arithmetic. We add and subtract stuff. We don't live fast enough to cross multiple orders of magnitude in almost anything we do. I mean, you might have a pound of bird. That's a big bird. But still, you're unlikely to have a 10-pound bird. Can you think of anything that you do that you might do 10 times in the world?
Space travel.
What's that?
It's space travel.
Space travel, but most of us don't do that. But that's the idea. So here we're starting to think about behavior that jumps multiples rather than adds some. Okay? This is the case when things don't happen on an annual basis. Organisms of different age groups are reproducing, they're continuously, and growth is not limited by resources. Sometimes things have, like annual plants, you know, the wildflowers when they come in the spring and the early summer, you're like, sweet. They only grow then, once a year. Humans, on the other hand, could have babies at any time. We're not annually organized, right? So we have continuous reproduction. Organisms of different ages are able to reproduce, and we can. And continuously means that they're able to do it at any given time, if it's available to them. And there's no limitation to resources. There's no feedback here, right? So we're going to run this with R max. That is our exponential growth rate. And then we dampen it later to slow things down. But let's go through the logic of getting to R max and why it acts like it does, so that we can then go back into logistic growth. Conditions that are required then: continuous growth, overlapping generations, and unlimited resources. This generation issue is again getting back to the idea of an annual plant. Annual plants, boom, reproduction, and then zero reproduction. And then the next spring, boom, they do it again. That's the annual compared to the continuous. When I say continuous growth, I don't mean they're getting bigger. I mean the population can grow continuously instead of the individual body size increase, right? So continuous population growth, overlapping generations, and key, unlimited resources. All right, let's see how this behaves with our model. With exponential growth, the actual amount of change does depend upon the amount present, because growth is characterized by a constant percentage that's being added. So here's my model. I'm going to add 0.1, or a 10% growth, to each of these initial populations. In that case, a tenth of 10 is 1. In this case, that would create 11. In this case, it's 4, and that would create 44. They have both grown with the same exponential rate of growth, but their actual change in size is different. That makes sense? It's a constant proportion of what's there. Okay, so let's take a look at this equation and see if it can make sense. The anatomy of the exponential growth equation. Here's the change in number over change in time, and so that's the rate of population change. And it is the result of, or the product of, the intrinsic rate of increase. That's the evolutionarily derived maximum rate that would be characteristic of populations when they have unlimited resources, and that means small size of the population because there's no demand for those resources. There's relatively low demand, right? And then here's the initial size. We need to know the number of individuals, right? So it's the product of the per capita rate and the number of individuals. So this is delta N, delta T. It's just with very small differences in time, right? R max is basically R running at full speed. That's our intrinsic rate. It's a maximum per capita rate of increase. This is an internal characteristic set by evolutionary history of the species. It's a constant fraction of the existing population added per time step. So is R max a constant or a variable? The answer is actually on the screen. It's a constant. We determine it for a species by doing those experiments where we make the n smaller and smaller and smaller and see how much they grow, and then we drive that curve in the r-axis and figure out what that maximum rate is. Say, okay, that is R max for buffalo. And we use them to model buffalo behavior, buffalo species management. Okay, so is there anything up here that bugs anybody? You're good. You're looking at a differential equation. Differential means difference, and the difference here is difference in n over time. And when you're using an instantaneous slope, that's called a differential equation. And that's one entirely fundamental feature of calculus. So a differential equation might be something that derives from, let me give you an example. This is really amazing. But imagine this, where you've got the velocity of a vehicle, and you've got time here. And the velocity, say, it ramps up really quickly, and it slows to it's braking, and it goes up like this, and goes back down like this. So this is, the velocity is the change in distance, right, over the change in time. So here we're plotting the derivative of space gives us velocity. And if we're tracking the slope of this curve, what do you get? The change in velocity over a change in time. What's that called? Think about when you're in your car, you're trying to enter the freeway. What are you doing? What's speeding up called? Acceleration. It's acceleration. So if you differentiate the velocity versus time curve, you get acceleration. So you can go from space to velocity to acceleration using that calculus approach. using this small slope differences. So you can jump across space to velocity to acceleration. And then there's a mathematical technique to go backwards. So that if you know the velocity, you can integrate the velocity curve and hit space. And so differentiation, this is A for acceleration. So differentiation goes that direction, and integration goes that direction. They're both calculus techniques. So if you went and integrated this curve, you would say, let's change from tracking the change in the number of individuals over time. Let's turn this curve into a curve that tells us exactly how many are there. So this is kind of like us going from velocity. That's our velocity curve. We're going to integrate it and go back to space. Rate of change in population size. When we integrate it, we go back to population size. So the integrated form of this curve looks like that. And you don't have to worry about how you get there. If you take calculus, you'll learn. But look what's on the left-hand side of the equation there. It's no longer change in size of population. It's what is the size of population? That's the one that looks like it, well, we'll get to it in a minute. But what it's saying is the number you have at any time t is the number you started with, cranked up by this expression right here. So the integrated form predicts the population at time t as a function of the initial number raised to an exponent. That exponential term, e to the r max times t, is saying I'm going to use an exponential model. I'm going to use the number e. That's the base of the natural log. You don't have to really worry about why they use that. It's just part of the definition of exponential behavior. And to the RT means we're going to use that r as a constant, and then we're going to add our t steps here, so that it starts with n naught. That's what that little 0 means, and then it grows every time we take time off. And the great thing about this is the integrated form tells us how many individuals there are. So the exponential growth curve reflects the species' ability, that is R max, to grow rapidly. Because R max is sitting up there in that exponential term. And if we use that, you can see that at any given time, we can plug in our time steps. Say we're the 4 or 5 time steps down, we know what we started with, we'll know what we have. So this back here is saying how rapidly is it changing and what direction. This over here is saying how many are present at any given time. What does exponential growth look like? Well, if it's completely unfed, imagine an organism that every female has 2. Well, then you're going to start with 2, and then you're going to 4, and then you're 8, and then 6, and you see how this goes. It is an extraordinary, and for bacteria, for insects, it could be every female has 1,000. And so this means that populations have the potential to just grow at absurd rates. And there are some examples where we've seen this. Here's an example where in Bennett in 1983, they went to these lakes in Scotland, in the Norfolk region of Great Britain, and they drilled down into the ponds. And they put these cores down into the ponds, they brought the sediments up, and they could age the sediments based upon the chemistry. And then they sliced them off in really thin layers and then analyzed the pollen in the layers. And from that, they were arguing that they could track the makeup of the trees that existed out there because those trees were contributing pollen. So when there's a lot of Scotch pine, you'd expect to see a lot of Scotch pine in the sediments of that age. And so what they did was they said, you know, this part of Scotland was buried under ice for a long time. And if you look at how long it's been since they've been exposed, either a short time or a long time, depending upon how far north you go, the further north you go, you get closer to the glacier. The glaciers were more recently covering Antarctica, right? So those would be younger areas. So when they looked at these things, they saw this extraordinary exponential growth in the Scotch pine. And here's a Scotch pine Christmas tree farm. See how nicely they're shaded. So people like their Christmas trees to look like, apparently. But Scotch pine are native to Scotland. And so there's an example, over 500 years, it grew exponentially. So that's pretty amazing. It indicates that the Scotch pine colonized a long time ago, but there was a post-glacial change in available habitat, unlimited resources as nobody else was around, and the glaciers pulled back and just exploded. But it can't go on forever. I mean, they're going to get to the point where resources become limited. And that really relates to body size. As Dan was saying earlier, here's the size of organisms, and here's their sort of Rmax values. It's not surprising to find out the viruses and bacteria have extraordinary intrinsic ability to increase. And then, as generation time, reflected by weight, gets larger, you can see that Rmax slows. And reflects the metabolism and development demands. You just can't get through the production of new offspring at any higher rate. So it makes sense that as we think about the way populations behave, that we tie those population behaviors into the identities of the organism. How do they reproduce? What are their body sizes? That reflects their resource demands. All sorts of logical reasons that populations behave differently. Here's an example of an interesting exponential phenomenon. The collared dove was released in Great Britain, and this is relatively recent, as you can see. It began to grow exponentially pretty quickly. But then, if you get up, say, 20-something years into the population expansion, and you fit an exponential model, using that equation back there that we had, dn dt equals R max times n, right? That was the rate at which things increased. It starts to fall off. What does that suggest? You can't possibly continue to speak that quietly. Nobody hears.
They take their capacity at some point.
Well, it suggests some sort of feedback in the system, right? What we think we could argue is that R is declining. R is not keeping up with R max. And the reason we think that might be the case is based upon resources, right? Okay, so we pick up on this same phenomenon right there, right there. You can see the same picture. On a different PowerPoint. Here I plotted the expected curve behavior, and then there's the differentiation. So it should have been up above 150, and you can see it was well below it. So it's getting some feedback, and they're beginning to believe that exponential growth that requires continuous reproduction, overlapping generations, unlimited resources doesn't happen very often. And if it does, it's pretty short-lived because there's just too high of a degree of demand. The reproduction potential is so high that you very quickly get so many organisms that resources are no longer in excess. So that puts us into logistic growth. Population growth that initially increases exponentially, but then levels out due to resource limitation. This we've been talking about already. We drew the curve. What are the characteristics of logistic growth? Well, it's got to be continuous reproduction. There are overlapping generations, but no longer unlimited resources. There are limited resources. And that means we can expect a population to behave like as if it were exponential when the population size is small, but then entail and experience more and more feedback that slows that growth down. It generates the S-shaped curve, or the sigmoidal curve, and it illustrates the leveling off of the population density over time. We've been through this. Any questions on it? Any comments? Sigmoidal growth is the shape that results from or the sigmoidal curve is the shape that results from logistic growth. And the reason they call it logistic is because it appears to jump from one value down here at the bottom way up to another value here, as if it had jumped by a multiple, like you'd get if you were taking a log. So that's the idea of a logistic growth. We talked about the carrying capacity. I think if you look at the PowerPoint or the PDF file, I think that says excess population. And I thought that was just confusing, so I edited it. I think we know what the carrying capacity is. It's the result. It results from all of the things in the environment that influence B and D, and it will result in a population level K where growth is 0. There's definition 2. We went over that idea that that's a population density. So it's not a characteristic of the environment, it's a characteristic of the population. Both of those are appropriate and logical. It's not the maximum. Talked about the overshoot. Here's some examples of where this really has been shown. You got to have Gauss, who's we'll talk more about from the 30s, who worked on both paramecium and yeast, and he grew yeast in these containers, and you can see that they grew up, hit carrying capacity, and here's an indication that they might have overshot it a little bit. Here's more of his work on paramecium. Look at this one bouncing around, like Kelly was saying earlier. What do you think K is on this one? Yeah, 400 is a pretty good guess. Somewhere in there. You can see it, and look at the way it cranks up in the early days when the population size is relatively low, and then you can see R starting to flatten out, and then R gets to 0 up here. So remember, it's the slope of this curve that's the rate of change. Look at how the slope is so high here. Why is it so low down there? It should be. This is the number per square centimeter, right? This is not number per individual. This is the total size of the population. So the reason it's low down here is there isn't very many of them around. So you got to pay attention to what's being plotted on the y-axis. This is really n, right? Rather than, and it's describing not, this slope is not describing R per se, because this is the total number of individuals. Remember, R is per each individual. So it has to be tweaked a little bit. The idea is the same, though. You can see periods of time with very rapid growth, and then it flattens out. And here's our barnacles that we talked about earlier in the distribution in the intertidal. And there's a good example of a K value somewhere around 75 or so. So the reason I've shown you this is that there are examples collected from the environment where you see logistic growth. And it occurs when there's something out there that must have created an opportunity for a population to begin when there wasn't one there before. What would that be? Because look, there was a time when it was really low. So the settlement of these larvae down onto places where there weren't barnacles before creates new populations. So these population growth phenomena occur when something creates a new gap and an environment is available and things start growing in there. Might be the flood that knocked down one of the cottonwoods, created a gap in the cottonwood forest, all the plants started growing. Or it might have been a boulder rolled on the beach, created new uncolonized substrate. And that's why I do start with a small number and then watch the population's vital characteristics change. So here's our logistic equation. And you'll see it in both of these forms. I like this one over here. But if you think about it as K minus N over K, well, K divided by K is 1. So you could reform it this way. You can use whichever one you want if it makes better sense to you. I like this one because I like to think of this one either less than 1 or greater than 1. this one is saying, is the difference between K and N positive or negative? If it's positive, it means N is smaller than K. And that term will be positive. Right? But if K is way bigger, or rather if N is far larger than K, then you get a negative number. And that would cause the thing to decline. I'd say we stick with this one. But it's up to you guys. You can do whichever one you want. You're really just modeling R using Rm with this dampening factor, right? So really R is changing, but this dampening factor is this guy here. What happened? Oh, yeah. And so this dampening factor, something that causes little dampening when N is small, but a lot when N is close to K, right? Because we want, when N is close to K, we want it to flatten out to 0. So here's a process by which I went through determining what's the most logical thing to put in there for the dampening factor. How did we get to the one we got to? But I don't really think we need to do this because we just went through it. I said, what about using just N over K? Throw N over K in there and see how it works. And then I ended up with 1 minus N over K, and it works really well. So you got this on your PowerPoint. Try using N over K and see what happens. See if it follows the sigmoid. And then you can end up understanding why 1 minus N over K is better. And then this is the same thing we just went through, where the change is related. This is the cool part here, is you can see exponential growth right there. dn dt equals R max times N. Constant percentage of N. Look at that. When I made these slides, I made them from the first edition of this book. And then I haven't taught this course for 15 years, 10 years. And then I picked these up again, and since then, they've gone through the book and captured all the mistakes. Look at that. Per capita rate of increase. That's not what R max is. What is R max? Anybody? It's the intrinsic growth rate. That's mislabeled. There were 2 or 3 of them that I didn't really catch when I was using. So that should be intrinsic rate of growth, right? And then there's that dampening factor. And then here's this same plot that we just went through, right? Down, if we look at the version in the textbook, they identify R max right there. It's the maximum rate of increase, R max, occurring when population size is really low. And we know it's actually derived from evolutionary behavior. And then over here you can see that when N is greater than K, R is negative and the population will decline. R changes with population size. 2, maximum rate, the intrinsic rate is associated with very low population sizes. And 3, when N equals K, growth stops. 4, when N is greater than K, R is negative. So those are the 4 characteristic sort of features of a logistic growth curve. That when N is really small, it acts like it's exponential, it runs at R max. As N gets larger, this feedback gets larger, and you get to the point where it doesn't grow. And if it gets too big, it goes negative. There's an example of the sort of plot that they use to figure out Daphnia's intrinsic growth rate and whether or not it behaves logistically. Daphnia is called a water flea, and they're very common in lakes. They are part of the food chain that filter-feeding fishes eat, and then the predatory fish eat those filter-feeding fish. Most anglers are going after the predators, trout. So these guys eat algae. And a lot of people working on lakes want to know what are the maximum rates at which they reproduce. So here, this investigators changed the number of Daphnia, and here you can see that they've done it in a stepwise fashion, doubling 2 to 4 to 8 to 16 to 24 to 32. So this is not arithmetic, right? This is a log, but what log scale? It's not going 10 to 100 to 1,000. This is log 2. This investigator doubled the size of the population every step, right? And look at that curve fit. That's pretty extraordinary. I mean, that is a really nice, that's suggesting that when you double the population, you'll see a linear relationship with the rate of increase, and you could probably use 0.3 for an R max for Daphnia. What did I do down there? Okay, I think this is a good place to stop for two reasons. One, we're about to run out of time, but also because I want to talk at the end here about human populations. But let me give you a bit of logistics. As I mentioned, I have a meeting, and Helen and I have to be at on Monday, so John Marin is going to excuse me, teach the course on Monday. What he will do is he will start the species interaction portion of the course. So he'll jump into the next section. And that species interaction will be describing, okay, how do we think about it when there are two different populations interacting with each other? How do we determine if that's of benefit for the two of them, or bad for both of them, or bad for one, or good for the other? And then talk about competition and niche theory. Then when I come back on Wednesday, we'll use Wednesday to mop up the human population growth, but also to review anything you want to review for the exam. The only way that becomes helpful is that if you study between now and then, because you won't know what you don't know until you look at your stuff, right? So try to force yourself to go over some of the material between now and next Wednesday. I will also ask some of your fellow students who did very well on the exam last time to talk about how they studied to make sure you have the opportunity to learn from your equals and maybe employ some of the same things. Okay? Very good.